So, friends, let us start the lecture number 22nd. And the title of that lecture is The Degree of Freedom and Constraints. You might have read these things already, but some detail and some other basic aspect of the degree of freedom and constraint I'm going to discuss. Anybody can tell me that what do you mean by degree of freedom? Degree of freedom.
So the number of
Yes, sir.
independent
Sir,
coordinates are required to specify the about a point, which tells about the point, the number of independent coordinates which are required.
Independent coordinates, no? Which
Yes.
yes, sir.
is required to.
And days.
Okay. Anyway, any other student? Let me know that what do you mean by degree of freedom?
So it is the number of independent ways by which a system can move without violating any of its constraints.
Achha. So what are the constraints? What are the constraints? Anybody else except Swati? Anybody else?
So the
So
limit
constraints,
Restrictions.
So constraints are the limitations of motion of a system.
Okay, very good. So these things I have to discuss. Number one point that the degree of freedom is that what are the freedom to move without violating the constraints or the limitation which has been set up for a particular motion. So what are the basic thing related to that I am going to discuss here. But before that, let us see that what are the external and internal forces. For example, if you are applying a particular force on a body, then one thing that you are giving a force to that body externally, but the internal particles also react in certain way, and that reaction may happen in such a way that they may cause the otherwise effect if they has not been balanced there. So that's why we should also think about the external and internal forces on a body. If externally we are applying a force, then what happened with the particles which are the constituent of that body and how they are reacting on that external force, that we should know. And according to that, if they are not balanced, then definitely they will show some otherwise effect on that body. So let us see that what are those and what should be for the balancing of such forces. The conservation theorem for the mechanics of a particle can be easily generalized to the case of a system of particles by taking care of mutual interactions. Now, if a mechanical system consists of two or more particles, then the force on the ith particle are given by this one. That is the Fi is equal to Fi external plus the summation over j is equal to 1 to n Fij. Means what this expression gives actually, कि if we are talking about the ith particle which is as a part of the constituent of that particular body, then first that particular particle will experience the external force, and then after what the internal particles are interacting with that to affect the position, effect, energy, and force of that particular ith particle. So if we will take the sum of these two, then we can realize that what the force has been experienced by the ith particle of that particular body. Where FIE is the external force acting on ith particle due to sources outside the system. Means that if we are applying the a force to the body, then ith particle, which is one of the constituent particle of that body, experiencing that force, and then after the interaction of other particle which is in surrounding to that. So that has been given by the summation term, and Fij that has been further elaborated here. Fij is the internal force on the ith particle due to the jth particle and the total internal force due to the all particle, that is J is equal to 1 to n, means that J is varying from 1 to n, and hence obviously if we are considering Fij, तो Fij means ith particle पर J इज इक्वल टू 1 से लेकर के n तक जितने भी विसिनिटी में या उसके सराउंडिंग या उस बॉडी के पार्टिकल हैं, दे विल हैव देयर इफेक्ट. एंड Fii, तो Fii में उस पार्टिकल का भी, पार्टिकल पर जैसे मान लीजिए I की तो कोई वैल्यू होगी ना, I की जो भी वैल्यू होगी उस वैल्यू के करस्पॉन्डिंग, यानी मान लीजिए अगर I की 3 वैल्यू हो तो F33 का मतलब हो गया कि जो एक्सटर्नल वाला फोर्स उसी बॉडी के द्वारा एक्सपीरियंस किया जा रहा है और सराउंडिंग के जो फोर्सेस हैं वो दूसरे वाले टर्म से दिया जा रहा है. द फोर्स ऑफ ith पार्टिकल ऑन इटसेल्फ इज नेचुरली जीरो, क्योंकि अपने ऊपर वो फोर्स, कोई भी बॉडी अपने ऊपर कौन सा फोर्स लगाएगी, वो तो जो भी फोर्स लगाएगी, जो भी इंटरैक्शन उसका होगा उसके आसपास के पार्टिकल पे होगा, उसके ऊपर कोई फोर्स नहीं लगेगा. According to the Newton's second law, if we will talk about this one, then obviously F internal is equal to the rate of change of the momentum on that particular particle, that is Pi dot. Pi dot means dpi upon dt, and this is equal to mi dvi upon dt. And we are talking about the ith particle only. That's why the suffix I has been taken for the mass as well as velocity, momentum, and force. So that will be equal to mi d2 ri upon dt2. That has been extended in the lower direction, lower dimension, you can say. Ki first we are taking the force, then momentum, then velocity, then one step down there, that is the Ri. And at all the time, we are balancing the equation by taking the differentiation. In the first part, if Vi is there, then the first order differentiation. And if we are taking Ri, then that is the second order differentiation, that is the balancing the equation. Now, when the sum is taken over all the particle of the system, equation number 1 takes the form, that is d2 upon dt2 and summation over I mi ri, that is equal to summation I fie and plus the summation I, and this summation j. I is not equal to j and Fij. I is not equal to j का मतलब ये हो गया कि I पार्टिकल नहीं होगा, क्योंकि वो स्वयं उस पार्टिकल को इंडिकेट करेगा. तो here we are taking this particular equation in elaborated form, which has been mentioned in the last slide initially. On the other side, on the right hand side of the equation number 2, first sum represents the total external force, that is F external, according to the Newton's third law, that any two particles of a system exert equal and opposite forces on each other. तो obviously अगर हमारा कोई एक पार्टिकल है, जितना फोर्स उसके ऊपर वो लगा रहा है उतना उस पर भी लगा रहा है, until and unless the body is not rigid body. अगर rigid body नहीं है तब सिचुएशन थोड़ी सी डिफरेंट हो जाएगी. If rigid body है, बॉडी अगर हम बात कर रहे हैं तो हमेशा हम rigid body की ही बात करेंगे. तो rigid body के केस में एक पार्टिकल जितना फोर्स उस पर लगाएगा न्यूटन के थर्ड नियम के हिसाब से, वो दूसरे पर भी वो उतना ही फोर्स लगाएगा. And hence what happen actually, they will balance to each other, and hence we will see here Fij plus Fji is equal to 0. यानी पहले के द्वारा दूसरे पर लगाया गया फोर्स और दूसरे के द्वारा पहले पर लगाया गया फोर्स, यदि उन दोनों का सम लेंगे तो that will be 0, because one is applying the same force on the other and vice versa. and hence the equation, what the equation 2 will get the shape, what type of shape will be there. Since the second sum in the equation number 2, that is sigma j I is not equal to j Fij, represents the internal forces in pairs, and for each pair the resultant force is 0. Consequently, the sum vanishes. And finally, the equation number 2 can be given as F external is equal to d2 upon dt2 summation over I mi ri. Means that what we are getting here, if the rigid body is there, then the internal forces are forces which are acting on each other by the constituent particle of that body or will vanish, and final force will be the external force experienced by each and every particle of the body. So this was the basic idea about the internal and external force experienced by the body. So let us have the another idea of the center of mass of reference. Center of mass of reference here. And inertial, actually, I will take the lecture especially for the center of mass reference and the laboratory mm, frame of reference system and correlation between them. And I think that the one lecture tomorrow, after tomorrow, for the lecture will be there, that will be dedicated on the center of mass and laboratory system. I will also try to solve some numerical problem related to that, so that I can conceptualize that what is the relation between the center of mass frame of references and the laboratory frame of reference system. Anyway, here just a brief of that I'm going to give the idea for the same. An inertial frame attached with a center of mass of an isolated system. The system has no external forces of a particle. It's called the center of mass frame of reference or C frame of reference. Actually, what the basic concept is there, the mass in in the center of mass frame of references experiences no external force. This is basic fundamental concept for that, and taking this particular concept, we will proceed to solve the problems related to that with the later on. In this frame of reference, the center of mass remains at rest, that is V is equal to 0, यानी वो मास अपनी जगह पे स्थिर है, मास नहीं मूव कर रहा है. अगर मूव करेगा तो पूरा सिस्टम मूव करेगा, पूरा रेफरेंस मूव करेगा. So that the total linear momentum of the system in C frame of reference is always 0, and that is P is equal to MB, and this is equal to summation over I mi vi. This is equal to 0 in the C frame of reference. You should always remember that if you are taking the center of mass frame of references, then in that case the momentum will be always 0, and that is P is equal to MB is equal to sigma I mi vi, that is equal to 0. This is why the C frame of reference is called the zero momentum reference frame also. This is why the C frame is called the zero momentum frame. So this idea we will use there when we will discuss the center of mass frame of references and its relation with the laboratory frame. Now let us see that what is the degree of freedom, what for this lecture is dedicated there. The minimum number of independent variable or the coordinate required to specify the position of dynamical system having one or more particle compatible with a given constraint is called the number of degree of freedom of the system. So means that if we are taking the liberty for the movement of a particular particle, then what the liberty is there regarding to the variable, regarding to the coordinates of that, that requires to specify the position of the dynamical system. Means that if any body is in a dynamic state, then what are the possibility to move in the different directions? What are the direction? What are the coordinates? And without violating the constant, what the constant has been given there. Any constraint example? Can you tell me what type of constraint you realize if we are discussing any type of motion? अगर हम कहें कि कोई एक एग्जाम्पल बताइए जिस एग्जाम्पल में कॉन्स्टेंट और मोशन दोनों का रिफ्लेक्शन होता हो.
सर पार्टिकल मूव
Yes,
इन अ
sir.
सर्कल.
Sir,
हाँ, तो क्या कॉन्स्टेंट होगा उसमें?
सर थीटा, मतलब इसका जो एंगल
थीटा-
होगा वो फिक्स होगा.
थीटा
Yes,
तो
sir.
वेरिएबल है. थीटा वेरिएबल
Radius
होगा.
will be- नहीं ओके नहीं सर, रेडियस उसका जो रहेगा वो तो
Sir,
फिक्स रहेगा.
radius
थीटा
will be
वेरिएबल.
यस 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 दैट इज. मतलब अगर आप
Sir,
मूवमेंट ऑफ
and this sir, yesterday's example. Sir, and yesterday's example of pulley.
हाँ,
Sir,
that
जो
is
कल आपने
also.
pulley का
हाँ, that
example.
is also means that we are
Yes,
taking the constraint. We are taking the constant means कि आप ये लिमिट डिसाइड कर दिए कि इसको ऐसे ही करना है. चलना तो है, लेकिन चलने में एक पक्ष उसका निर्धारित कर दिए कि इसके आगे नहीं जा पाए. जैसे एक खूंटे में गाय बंधी हुई हो, तो वो एक मैक्सिमम उसका जो मूवमेंट होगा एक सर्किल में होगा, उसकी रेडियस उस रस्सी के बराबर होगी जिसमें वो गाय बंधी होगी. तो उसका जो कांस्टेंट हो गया, वो कांस्टेंट हो गया कि इस रेडियस से आगे वो नहीं जा सकती. बट इन दैट द काउ कैन मूव हियर एंड देयर एंड if we are talking about the angular motion, then at all the time the theta will vary. तो थीटा यहाँ एक वेरिएबल होगी, बट वो कांस्टेंट हमारा r हो जाएगा कि r से आगे नहीं जा सकता. तो अगर हम इस तरीके का वेरिएबल डिसाइड करें जो कि कांस्टेंट को ओबे करता हो, कांस्टेंट के साथ कंपैटिबल हो, तो जो वो जिस फ्रीडम में वो थिंग मूव कर सकती है, that is known as the degree of freedom. Let us have certain example for the same. Let us have the first example, that moving particle freely in space described by a set of coordinates, that is simply the Cartesian coordinate. कि अगर स्पेस में आप कोई पार्टिकल रख दिए, ऐसे हाथ से हवा में एक पार्टिकल रख दिए, तो वो एक्स डायरेक्शन में जा सकता है, वाई डायरेक्शन में जा सकता है, जेड डायरेक्शन में जा सकता है. यानी उसको कंप्लीटली हम डिफाइन करने के लिए हमें 3 कोऑर्डिनेट की जरूरत होगी. तो ऑब्वियसली वी विल से दैट देयर इज द डिग्री ऑफ फ्रीडम दैट पोजेस्ड बाय दैट पार्टिकल इज इक्वल टू 3. अब एक्चुअली यहाँ पर हमने कोई कांस्टेंट नहीं डिसाइड किया, केवल एक कांस्टेंट डिसाइड कर दिया कि पार्टिकल शुड बी ऑलवेज इन एयर, दैट इज इन स्पेस. वो किसी सरफेस पे नहीं होगा. अगर वो किसी सरफेस पे हो गया तो ऑब्वियस सी बात है कि आपने उसको कांस्टेंट दे दिया. जैसे हम ये कह दें कि फ्लोर पर कोई बॉल मूव करनी है, तो फ्लोर पर अगर कोई बॉल मूव करनी है, उसकी फ्रीडम है, तो एक्स डायरेक्शन में मूव करेगी या जेड डायरेक्शन में मूव करेगी. अगर फ्लोर पर ही रहना है, यानी फ्लोर पर रहना एक कांस्टेंट हो गया उसका, यानी वो जेड डायरेक्शन में नहीं जा सकती है. बट इफ यू आर टॉकिंग अबाउट द पार्टिकल इन अ स्पेस, then there is the liberty to move in z direction, then x direction, then y direction. So I think have you clarity for this or not? Anybody have any problem to understand this one? Okay.
No, sir.
Let us have the second example. For two particles having the coordinates x1, y1, z1 and x2, y2, z2, so there will be the 6th degree of freedom. There will be the 6th degree of freedom. जैसे हम ये कहें कि एक मॉलिक्यूल है, उस मॉलिक्यूल में 2 एटम है मान लीजिए, और वो बीच में ज्वाइंट नहीं है. तो ऑब्वियस सी बात है कि पहले और दूसरे एटम के बीच में जो लिबर्टी है, वो 3 लिबर्टी इसके लिए है स्पेस में, 3 लिबर्टी उसके लिए है. यानी एक्स वाई जेड डायरेक्शन में उसकी लिबर्टी है और इसकी लिबर्टी है. तो दोनों को अगर हम एक साथ कंसीडर कर दें तो हमें कहेंगे कि 6 डिग्री ऑफ फ्रीडम दोनों के साथ अटैच है. लेकिन अगर उन दोनों में से एक हम ऐड कर दें, यानी उनको एक दोनों एटम को जोड़ करके एक मॉलिक्यूल कर दें, तो मॉलिक्यूल बनने में क्या होगा कि ऑब्वियस सी बात है उसके अंदर बॉन्डिंग होगी. जिस एक्सिस पर उसकी बाउंडिंग होगी, वो लिमिटेशन हो गई, वो फिक्स हो गई, वो फिक्स हो गई तो वो दोनों में कॉमन हो गई। तो ऐसे में उसकी डिग्री ऑफ फ्रीडम रिड्यूस हो जाएगी इन कंपैरिजन टू द इंडिपेंडेंट कोऑर्डिनेट when they were not joined to each other, they were independently in the space. So that's why this degree of freedom is important to visualize a particular particle ki where it is and what is the possibility and liberty to move that particular particle in the space or any constraint situation. So some other example you can see in the textbook of the Rana and Jog already. एक किताब और है इसकी. अब तो most of the people, I think you people are having the book of the J.C. Upadhyay that has been written in Israeli language. Even then, if you can see the more example, then there is the book of Rana and Jog that you can see there. Let us have the configuration space. What is the configuration space? The configuration of a system of n particle moving freely in space may be represented by the position of a single point in 3n dimensional space, which is called the configuration, space of the system. Let us try to understand this one. हमने क्या कहा? हमने कहा कि भाई n particles हैं और सारे के n particle they are free to move in the space हैं. तो ऑब्वियस सी बात है कि अगर हम उनको रिड्यूस करना चाहें कि हम एक पॉइंट की क्या लिबर्टी हो सकती है, भाई एन पार्टिकल की 3 लिबर्टीज हैं, हर पार्टिकल की अगर इंडिपेंडेंट है तो, और अगर हम कह दें कि इसको हम एक पॉइंट सिंगल पॉइंट से रिप्रेजेंट करना चाहते हैं तो ऑब्वियस सी बात है कि वो ऐसा पॉइंट होगा कि जिसकी फ्रीडम या लिबर्टी 3n होगी. हम कह दें या हम ऐसा कह दें कि n पार्टिकल की 3 लिबर्टीज हैं, यानी n पार्टिकल में सभी n पार्टिकल्स की 3 डिग्री ऑफ फ्रीडम. तो ऑब्वियस सी बात है कि अगर इनको जोड़ेंगे तो 3n आ जाएगा. लेकिन हम कह दें कि corresponding to all we are representing it by a single particle and that single particle have the liberty to move in the different direction, that is a 3n, then that is known as the dimensional space, and that dimensional space is known as the configuration space of the system. Just this is the projection of n particle by a single particle denoting its degree of freedom in the space. For example, one particle can move freely in 3 dimensions. And for a system of 2 freely moving particle, that is equal to 6. जैसे हमने बताया कि अगर भाई एक पार्टिकल के लिए 3 लिबर्टी है, 3 डिग्री ऑफ फ्रीडम है स्पेस में, तो 2 पार्टिकल की 6 हो जाएगी. ऐसे ही हमने यहाँ अगर n की वैल्यू हमने 2 ले लिया तो ऑब्वियस सी बात है कि 3 into 2 हो जाएगा. तो पूरी की पूरी जो 6 dimensional space हम मान सकते हैं corresponding to the single point. So that is known as the configuration space of a system. In the latter case, the configuration of a system of 2 particles can be represented by the position of a single point with the 6 coordinate in 6 dimensional space. Are you following this point or not? Let me know. If anybody have any confusion, then let me know so that I can elaborate, I can try to reduce the confusion of a particular story. Anybody have any?
Yes,
in
sir. So in the last case, the latter case that you are explaining, so it is in 6 dimensional. Why can't we take it in a 3 dimensional with 2 particles?
Actually, 2 particle, if we are taking the 2 particle and each have the 3 degree of freedom. Now, there are the 6 directions. You have 6 dimensions corresponding to 2 points. And if we are taking that only 1 point is there and that is representing those earlier two particles, then the particle must have liberty to move on all 6 dimensions. That has been mentioned here. And that 6 dimensional space is known as the configuration. कुल मिला करके यहाँ कहना ये था मेरा, या इस टेक्स्ट का निहितार्थ केवल इतना है कि हम जो पार्टिकल थे उनको कॉन्फ़िगर कर रहे हैं एक सिंगल पॉइंट के रूप में, कि हमारे पास दो पार्टिकल थे, तो दो पार्टिकल मान लीजिए आपने स्पेस में ले लिया और वो तीन दिशा में, अलग अलग तीन दिशा में चल रहे हैं, तो कुल मिलाकर के 6 दिशाएं उनकी चलने की हो गई। अगर कोई ऐसा पार्टिकल हम ले लें जो 6 डायरेक्शन में, 6 डायमेंशन में चल सके, तो वो उन दोनों पार्टिकल को साइमल्टेनियसली रिप्रेजेंट करेगा। दैट इज नोन एज द configuration of two particles in a space by the single point. That is the configuration space. Are you following or not?
Yes, sir.
Okay. This system has 6 degrees of freedom and its configuration space is 6-dimensional. The number of coordinates required to specify a dynamical system can be reduced under the certain constraints. And now we will discuss those constraints there. But before that, we will discuss some more aspects related to. Hence, the degree of freedom of a dynamical system is defined as the minimum number of independent coordinates are variable required to specify a system compatible to the constant. तो अगर हम इसके लिए इसको मैथमेटिकल फॉर्म में देखें, तो if there are n independent variable, say the q1, q2, q3 up to qn, and n constraints are there, then constraints will be c1, c2, c3 up to cn, then such that we will have I is equal to 1 to n and ci dqi that is equal to 0 at any position of a system. Then we must have that C1 is equal to C2 is equal to C3 is equal to Cn is equal to 0, because dqi will never be equal to 0. So some constraints are there, that constraint we have to discuss here. The limitation on the motion of a system are called the constraints, and the motion is called, is said to be the constraint motion, constrained motion. कि अगर हम एक लिमिटेशन लगाएं किसी मोशन के लिए, तो हम कहेंगे उसी लिमिटेशन को ही कहते हैं कि ये कांस्टेंट है। ये कांस्टेंट है भाई कि आज हमें ये क्लास लेनी है, इसके बाद ही हम फुर्सत में हैं, इसके पहले हम फ्रीडम मेरी नहीं है, ये मेरा कांस्टेंट है आज का। और अगर हम उस कांस्टेंट के चलते कोई काम कर रहे हैं, अगर मोशन की बात करते हैं तो वो कांस्टेंट मोशन होगा। एंड अगर हम कोई काम कर रहे हैं, कोई भी वर्क कर रहे हैं, तो दैट इज द कांस्टेंट वर्क, कि इस लिमिट में, इस लिमिटेशन में, इस कंडीशन में, इस एनवायरनमेंट में हमको ये काम करना है। तो दिस इज द लेटरल मीनिंग ऑफ द कांस्टेंट. So that has been divided into two parts, that is a holonomic constraint and non-holonomic holonomic constraint. Let us see that what are the holonomic constraints. The constraints limit the motion of a system and the number of independent coordinates needed to describe the motion is reduced. Actually, whenever the constraint will be there, then that constraint or will reduce the independent number of coordinates which is required to describe the motion. क्यों? जैसे मैंने आपको एग्जाम्पल लिया कि अगर मॉलिक्यूल बनने के पहले दोनों एटम हैं, तो उन दोनों एटम की अलग अलग डिग्री ऑफ फ्रीडम होगी, इंडिपेंडेंट कोऑर्डिनेट्स होंगे, और तीन उसके 6 हो सकते हैं। लेकिन अगर वो आपस में ज्वाइंट कर लिए सिंगल बॉन्ड के थ्रू, तो हो सकता है उस सिस्टम की जो डिग्री ऑफ फ्रीडम होगी वो 5 हो जाएगी, एक कॉमन हो जाएगी दोनों के बीच में, और दो उनके अलग से फ्री स्पेस में मूव करने की संभावना होगी। तो ऑब्वियसली कि अगर हमें एक कांस्टेंट लगाए, तो देखो इसकी डिग्री ऑफ फ्रीडम या इंडिपेंडेंट कोऑर्डिनेट्स इसके रिड्यूस हो गए। फॉर अ मोशन ऑफ अ पार्टिकल in a circle, whatever you were telling the example, so that we are having here, for a motion of a particle in a circle, only one coordinate is sufficient to describe the motion, that is q1 is equal to theta, because the radius a of the circle remains constant. Only the variable is theta. Whatever the change is theta, according to that, different destination will be there at the circumference of the circle. So, but at all the time, What about the point at the circumference? That will lie at the same distance from the center of that circle. So that's why that is the constraint that our particle, our system, whatever the situation we are considering at the boundary of the circle, that have to obey the constant that it has not to leave the distance more than a from the center of that particular circle. So if r is the position vector of the particle of any angular coordinate theta relative to the center of a circle, then we will define it that the mod of r is equal to a, यानी जो maximum value r की हो सकती है वो that will be equal to a, and a will be always less or equal than r. So obviously if this is equal to at all the time, if we are considering the particle is always at the boundary, then at all the time this r will be equal to a and this r minus a will be equal to 0. This is the constant for that. Above relative नहीं होगा, relation होगा. Above relation is known as constant for the particle in the circular motion. Let us correct it. So above relation is known as constant for the particle in circular motion. The particle moving on the surface of a sphere can be specified by the spherical coordinate. कौन-कौन से होंगे? R होगा, theta होगा और phi होगा. Where theta and phi may vary, R remains constant at all the time. Why? Because even if we are specifying a particular sphere and talking about the surface of a sphere, then the existence of the surface of a sphere will be only if a particular r will be there that is creating the surface of that sphere. Without that, it is not possible to have the shape of that sphere. That's why this r remains constant in case of the spherical notation of a particular system, while theta and phi may have liberty to vary for the same. That's why here we have the constraint for r if that is the radius of that sphere, then that will give the limitation for anything if it try to move at the surface or inside that particular sphere. Therefore, if we will talk about the number of coordinates or the degree of freedom related to the spherical system, whatever we are considering in this case, that q1 is equal to theta and q2 is equal to phi are two independent coordinates, because as a constraint, the radius of the sphere A is constant. That is, this mod of r is equal to a. This r is the position vector. Means that if the particle is lying at the surface, then obviously that has to be measured from a particular point. No? So if we are taking the center as the origin, then obviously the position of the particle at the surface is lying. That gives the idea about the radius vector. Means that the position, distance, and if we are taking it just as a vector quantity, then it will also represent the direction of the same. So mod of that will be equal to a. In circular motion, this mod of r is equal to a, and only one independent coordinate theta will be there, and due to that we will have, suppose the constraints are present in the system of n particles, then if the constants are expressed in the form of the equation of the form that is r1 r2 up to t that is equal to 0, then they are called the holonomic constraint. Means that if we are considering the constant in the way what has been represented here, then the system or system's limitation is known as the holonomic constraint. Let there be the m number of such equation to describe the constants in n number of particles of a system, then obviously now we may use this equation to eliminate m of 3n coordinates, and we need only the n independent coordinates to describe the motion, and that may be given by 3n minus m. Just I was giving the example of the molecule and particle which are constituting to that. Then if they are joining by one arm or one bond has been aligned in a particular direction, then that will be reduced from that. And before that, if we will talk about two independent atoms, then n will be 2 for two atoms, and 3 is corresponding to their liberty in the space, and there will be the 6. And if we will have one common bonding between them, means that one direction will be the common, then m will be equal to 1, and total n will be equal to the 5, and this is known as the degree of freedom for the same. The system is said to be said to have n or 3n minus m degree of freedom. For already I have explained in case of molecule. The elimination of the dependent coordinates can be expressed by introducing the n is equal to 3n minus m. Here independent variables are q1, q2, q3 up to qn is there. These are referred as the generalized coordinates. Already you have the one independent topic in your syllabus. You follow the generalized coordinate and how we can have the idea about that. I will take one more lecture for the generalized coordinate, how to refer to the different system and points as well as the particle to describe in terms of the generalized coordinates. Let us have the superfluous coordinates. Superfluous coordinate का क्या मतलब हुआ भाई? कोई आप लोगों को पूछता है? Superfluous coordinates. Superfluous coordinate.
No idea, sir.
अरे इस शब्द के बारे में नहीं सुना है आप लोगों ने?
नो सर।
पहली बार सुन रहे हैं।
Redundant शब्द सुना है? Redundant नहीं।
No, sir.
अच्छा, सुपरफ्लुअस मीन्स कि जो वास्तव में यूजलेस टाइप का हो, कहते नहीं कि सुपरफिशियली आप बात कर रहे हो। सुपरफिशियल तो सुने हो ना? नहीं।
Yes, sir.
Yes.
तो सुपरफिशियल
Yes, sir.
ही सुपरफिशियल से ही ये सुपरफ्लुअस वर्ड डिराइव्ड है। इसका एक मतलब होता है रिडंडेंट। रिडंडेंट बहुत केसेस में वहां इस्तेमाल होता है, जैसे लाइन डिस्ट्रीब्यूशन होता हो। तो आप लोग देखे होंगे कि कभी कभी पहले जो बिजली के खंभे होते थे ऊपर से उस पे सप्लाई दी जाती थी, लेकिन क्या होता है कुछ समय के बाद उसको अंडरग्राउंड कर देते हैं केबल के थ्रू, तो और बहुत दिन तक वो ऊपर पड़ा ही रहता है, ऐसे ही उसमें कोई सप्लाई नहीं होती है, तो उसको कहते हैं रिडंडेंट लाइन। वो रिडंडेंट लाइन होती है। या हम कहें कि किसी लूप में कोई चीज पड़ जाए और उस लूप में पड़ने के बाद उधर का कोई यूज ना हो, तो दैट इज द रिडंडेंट पार्ट। जैसे कभी कभी नदियों में डेल्टा बन जाता है, तो डेल्टा मैंने पहले उधर से नदी बह रही थी और उसका वेग बहुत अच्छा हुआ तो काट करके सीधा कर दिया, लेकिन एक जो कर्व बना हुआ है वो रिडंडेंट पाथ ऑफ दैट रिवर होता है। तो दैट इज द वर्ड दैट हैज इट्स यूजुअल मीनिंग फॉर द सुपरफ्लुअस हियर। तो ऐसे ही कभी कभी ढेर सारे ऐसे कोऑर्डिनेट्स होते हैं जिन कोऑर्डिनेट्स की जरूरत ही नहीं होती है, वो सुपरफ्लुअस होते हैं या वो रिडंडेंट होते हैं, लेकिन वो किसी भी कैलकुलेशन या किसी प्रॉब्लम के रियलाइजेशन में प्रॉब्लम क्रिएट करते हैं, तो उनको समझना और जानना बड़ा जरूरी रहता है। तो आई एम ट्राइंग टू गिव द आइडिया अबाउट दैट। The idea of degree of freedom makes it clear that when we are using say rectangular Cartesian coordinate, we have several redundant or superfluous coordinates if there are holonomic constraints there. This redundant and non-independent. The independence of the coordinates make the problem complicated, and this difficulty is resolved by using the generalized coordinates. That's why this generalized coordinate is important to understand, and this is important to apply for the exact visualization of the degree of freedom and motion of a particular particle in a certain constraints. For example, let us consider a body be thrown vertically upward with the initial velocity v0. तो इसके लिए क्या इक्वेशन लगाएंगे हम लोग भाई? अगर हम v0 हाँ सेकेंड इक्वेशन लगाएंगे जो s इज इक्वल टू ut प्लस हाफ vt स्क्वायर या माइनस हाफ gt स्क्वायर, इस तरीके से जो इक्वेशन थी वो इक्वेशन लगाएंगे. तो आइए देखते हैं कैसे उसमें हम इसको एक्सप्लेन करने की कोशिश करते हैं. कि हमने क्या किया कि एक बॉडी लिया, उसको हमने वर्टिकली अपवर्ड डायरेक्शन में फेंक दिया, एंड दैट हैव इट्स इनिशियल वेलोसिटी दैट इज इक्वल टू v0. द बॉडी विल मूव इन द स्ट्रेट लाइन इन कार्टेशियन कोऑर्डिनेट और विल बी रिप्रेजेंटेड एज, कैसे रिप्रेजेंट करेंगे? ऑलरेडी यू पीपल हैव read it that कि x is equal to 0 and y डायरेक्शन में आपने उसे उछाला है, ऊपर की तरफ थ्रो किया है, तो ऑब्वियसली वो स्ट्रेट अपवर्ड डायरेक्शन में जाएगी. तो y इज इक्वल टू v0t माइनस हाफ gt स्क्वायर, एंड देयर इज नो मोशन अलोंग x direction or along z direction, and we will see here where x and z axes are the horizontal and y axis is the vertical direction. जैसे हमने 3 एक्सेस लिया तो हॉरिजॉन्टल में 2 हैं, एक x डायरेक्शन में एक x डायरेक्शन में एक z डायरेक्शन में, y डायरेक्शन को हमने अप डायरेक्शन मान लिया है यहाँ पर. तो y आपका ऑब्वियसली द वर्टिकल डायरेक्शन होगा. At different values of t, only y coordinate varies and x as well as the z coordinate remains the same. Therefore, x and z are the superfluous coordinate in this case. In conclusion, we need only one coordinate, that is q is equal to y, to describe the vertical motion of a system here. So what you are seeing here, usually if we are talking about the motion of a particular particle, then we used to say that there will be the in the space there will be the 3 coordinates or the 3 degree of freedom for its motion. But if you are talking about the vertical motion specifically here, then y, z and x remains constant, and there will be no change in that. Then this will be just the redundant coordinate or the superfluous coordinate. Only one coordinate will be sufficient to have its position at a different time in the space. So that's why sometimes we need to see that, realize that what the situation is prevailing with that particular particle which is under motion. Let us have the non-holonomic constraint. What is the non-holonomic constraint? Motion of a particle placed on the surface of a sphere of radius a will be described by, अब देखो r की वैल्यू यहां पर ये r की वैल्यू ग्रेटर देन a, r माइनस a इज ग्रेटर देन a. ये तो मैं थोड़ा सा डाउटफुल लग रहा है. It should be always less than that. Just check me कि either I am right or wrong. क्योंकि अगर हम रेडियस की बात करें, किसी भी अगर हम रेडियस की बात कर रहे हैं, तो रेडियस की बात अगर हम कहें तो although it has been mentioned here r is greater or less than a, or r minus a is greater or equal, greater or equal to the 0. Already it has been described here in the same way and the text. The constraint which are not expressible in the form of f of r1, r2 up to t is equal to 0 are called the non-holonomic constraints. Already you people might have seen one condition here. This condition, if the constraints are expressed in the form of equation that of the form that is f of r1, r2, r2 up to t is equal to 0, then that is under the holonomic constant. And if that is not obeying this system, or that is not obeying this particular condition, then those are in the category of the non-holonomic. For example, the motion of a particle placed on the surface of a sphere of radius r will be described by r, that is the mod of r will be greater or equal than a, greater or equal than a. R minus a is greater or equal to the 0. And just we are taking another example here कि the gas molecule, जैसे इससे ज्यादा clear हो जाएगा आपको, the gas molecules in a container are constrained to move inside it, and related constraint is another example of non-holonomic constraint. जैसे हमने कहा कि कोई गैस है किसी एक कंटेनर में रख दी गई और उसमें उन मॉलिक्यूल्स का मूवमेंट हो रहा है, तो उसका जो मूवमेंट है वो नॉन होलोनॉमिक कॉन्स्ट्रेंट के अंतर्गत आएगा. कैसे आएगा ये तीसरे पॉइंट पर ट्राई किया गया है समझने के लिए. फॉर द गैस मॉलिक्यूल इन द स्फेरिकल shape or with the radius a and r is the position vector of the molecule, then the condition of the constraint for the motion of molecule can be expressed. भाई अगर हम ये कहें कि जो मॉलिक्यूल है वो मॉलिक्यूल सरफेस, कभी कभी आपने अगर काइनेटिक थ्योरी ऑफ गैसेस को पढ़ा होगा तो जो किसी भी वेसल का प्रेशर होता है वो इस बात पे डिपेंड करता है कि हाउ द गैस मॉलिक्यूल्स आर स्ट्राइकिंग एट द वॉल्स ऑफ दैट कंटेनर. बट स्ट्राइकिंग मींस दैट कि they are not just going to strike just as a ball to that particular body. They are reaching to the boundary and transferring the momentum, and they are coming back to that. Or in other words, you can say that just they are approaching to the boundary, and before that imparting the momentum, they are coming back to that. Means that they will never achieve, rarely they will achieve the boundary. Before that they have to be rebound. That's why this condition has been given here कि जो R है यानी उनकी जो पोजीशन है वो पोजीशन A से कम होगी या रेयर केस में उसके बराबर होगी, या हम यूं कहें कि R minus A is less or equal than 0. This condition is not obeying the expression what we have taken कि F R1, R2, R3 up to T that is equal to 0. That's why they are in the category of the non-holonomic constraint. या दूसरे शब्दों में यूं कह लीजिए कि मॉलिक्यूल उसके बीच में ही चल सकता है, उससे कम दूरी पर, ज्यादा दूरी पर दाएं भी चल सकता, बाएं भी चल सकता. इसके लिए कोई ऐसा कॉन्स्ट्रेंट नहीं है जो एग्जैक्टली आप किसी डोरी में बंधे हुए पत्थर को घुमाते हुए आप जिसकी कल्पना कर सकते हो, ऐसा कॉन्स्ट्रेंट यहां पर उस मॉलिक्यूल के लिए नहीं है. एंड दैट इज ऑलवेज रिस्ट्रिक्टेड बाय द इक्वेशन और द एक्सप्रेशन दैट हैज बीन मेंशन्ड हियर इन द last bullet point. That's why this is the best example of the non-holonomic constraint. Similarly, we will talk about the above situation कि जैसे हम कहें स्फीयर है, स्फीयर का रेडियस a हमने ले रखा है और r उसका पोजीशन वेक्टर है, तो r उसका पोजीशन वेक्टर ग्रेटर देन a या r माइनस a इज इक्वल आर ग्रेटर देन 0, ये दोनों का डिफरेंस जो दिया गया है कि भाई जैसे हम ये कहें कि आर उसकी मैक्सिमम मूवमेंट या मैक्सिमम उसका पोजीशन का मेजरमेंट है और आर उसकी रेडियस है, तो दोनों के डिफरेंस को इस तरीके से अगर हम यहाँ पर एक्सप्रेस करते हैं तो दैट इज इन द कैटेगरी ऑफ नॉन होलोनोमिक कांस्टेंट. So this is all about what I was interested to discuss today's lecture. Anything else if you want to discuss? Otherwise, our time is almost over.
In the previous slide, the
हाँ,
last point, sir, it is confusing. Sir, it is
कौन
showing
वाला?
that R is the position vector and A is the radius of that molecule. So
हाँ,
how is R smaller than or equal to A? I mean, sir, R should be greater or equal to A, no?
Actually, एक मिनट, क्या है कि for the gas molecule in the spherical shape with the radius A and R is the position vector of the molecule, then the condition of the constraint for the motion of the molecule can be given as कि R A is greater or less than the position R.
Yes,
एंड
sir.
यानी आपका कहने का मतलब यहाँ पर ये है कि ए तो मॉलिक्यूल का रेडियस है, ये ना बात कर रहे हैं आप?
Yes, sir. Yes, sir. A radius है मॉलिक्यूल का और R पोजीशन वेक्टर है. तो सर पोजीशन वेक्टर A से बड़ा होगा ना कि रेडियस सर पोजीशन वेक्टर से
एक्चुअली
बड़ा होगा.
यहाँ पर ए उस मॉलिक्यूल का नहीं है बेटा, ए
Yes,
उस
sir.
मॉलिक्यूल का रेडियस नहीं है. देखो लिखा
Yes, sir.
है कि फॉर अ गैस मॉलिक्यूल इन द स्फेरिकल शेप विद द रेडियस ए, उस जो स्फेरिकल शेप का हम एक वेसल ले रहे हैं जिसमें ये रख रहे
अच्छा,
हैं,
yes, sir.
हम
Okay,
उसकी
sir.
बात कर रहे हैं. दैट्स
Okay,
व्हाई
sir.
दैट
Okay.
कंफ्यूजन यू हैव हियर ना.
Okay, sir. Thank you, sir.
तो आई थिंक आई शुड टेक द अटेंडेंस ऑफ यू पीपल ना. तो आकांक्षा द्विवेदी,
Present, sir.
अटेंडेंस प्लीज. ओके. अमृता गुप्ता,
Present, sir.
दीपमाला,
Present, sir.
देवेश,
Yes, sir.
धारिणी,
Present, sir.
Present,
गौरव,
sir.
गौरव,
Yes, sir.
ज्योति,
Yes, sir.
Present, sir.
ज्योति,
Present, sir.
निधि, एब्सेंट, साक्षी, साक्षी सिंह, ये साक्षी सिंह भी नहीं आती क्या भाई? क्यों धारनी, साक्षी आती कि नहीं?
Sir, she has only come on the orientation day. उसके बाद वो कभी नहीं आई.
न साक्षी आई न निधि आई, दोनों नहीं आई ना.
सर निधि तो आती है बट साक्षी नहीं आती है. साक्षी कभी नहीं आई.
ओके.
Yes.
कुमारी अंबिका,
Present, sir.
ममता, मयंक मिश्रा,
Sir.
प्रतिभा, प्रियंका सिंह,
Present, sir.
प्रियंका त्रिपाठी, प्रियांशु श्रीवास्तव,
Yes, sir.
रजनीश कुमार सिंह,
Present, sir.
सौरभ मिश्रा,
Present, sir.
शिवम,
Yes, sir.
श्याम जी,
Yes, sir.
सोनू कुमार,
Yes, sir.
सुरभि शर्मा,
Present, sir.
सूरज, स्वाति,
Present, sir.
तान्या,
Present, sir.
वैभव,
Yes, sir.
विनय,
Yes, sir.
किंजल, Kinjal, Ashwani,
Yes, sir.
Mayank, Mayank Kumar Swastav. Anyway, so tomorrow I will take the lecture on the stability and equilibrium. That will be very interesting. I will try to solve one very good example. That is a numerical problem. So please join timely. Then we will see that. That's okay. Thank you very much.
Thank you, sir.
Okay, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So,
हाँ बताओ.
so yesterday we were studying